Welcome to Programming in Modern C++. We are going to discuss tutorial 8 on how to design a user defined type like the built in type. We had started discussing this in the last module, in the last tutorial, in tutorial 7, where we analyzed the difference between built in types and UDTs and discussed what is the meaning of building a data type and understood the necessary build process and built a fraction data type by iterative refinement. Continuing on that, we will build two more UDTs in this tutorial, int n and poly t, and we will try to now mix these UDTs that we have built. So, this is the outline which will be there on the left all the time. Let us first talk about int n UDT. Int n UDT has two purposes. One is to build a data type that is like the int data type in the built in int integer data type of C++, and in the process understand some finer details regarding the int data type itself. So, we are familiar with int as a signed integer. We know that it is represented in a given number of bits, typically 8 bit, 16 bit, 32 bit, 64 bit or even 128 bits. In our desktops and servers, we mostly work with 32 and 64 bit, but 8 and 16 bits are also popular in different embedded systems. 128 bit used in very high end applications, which need really large integer numbers. Now, we know that for the int type, there are two constants that are defined in the system, from which you can really know what is the size of this integer and what is the range of values that the int is going to represent. For example, if you are using 32 bits, then int max, the maximum integer that you can represent, is naturally 2 to the power 31 minus 1, which is this number 2147483647, and int mean, the minimum number or the maximum negative number that you can represent is minus 2 to the power 31, which is this number. Naturally, on the positive side you have one number less, because 0 is counted on the positive side. Beyond this int max, int min range, we get integer overflow and numbers wrap around. So, what does that mean is, if you just write a very simple program to analyze this, you will see that you can print int max and int min, which on a 32 bit system I am showing this. It gives you the above values, but if you try to print int max plus 1, if you want to have one number more than that, then it actually wraps around the maximum and comes to the minimum. So, here you have int max and here you have int min. So, this is 2 to the power 31 minus 1, this is minus 2 to the power 31. So, if you do plus 1, then instead of going here, instead of giving you 2 to the power 31, it wraps around and gives you minus 2 to the power 31. That is the basic wraparound process of finite bit representation that we have. I mean, no matter how many bits you have, you will always have this property too. Similarly, if you try to decrement, subtract 1 from int mean, the minimum negative number, it will wrap around in the reverse way, in the opposite way, and give you the maximum positive number. And very interestingly, if you try to take the negative of minus int mean, you will get int mean itself, right. You will not get a positive number, because the minus int mean does not has to be plus of this, which does not have a representation, which is this plus 1, which basically, as we have seen, boils down to int mean, right. So, these are the boundary values that you can see is where the numbers will behave differently from what you expect in the arithmetic to happen, right. I am sure you had known this, but I just wanted to highlight. So, given this, if you want to build an integer type, signed type with a given number of bits, that you want, that I want this many bits and I want this integer property to happen within that bits. So, let us say that we want to build an integer having n number of bits, where n of course is a given constant. So, naturally we can very easily understand that mean int, which is the minimum integer you can represent, will be minus 2 to the power n minus 1, and max int will be 2 to the power n minus 1 minus 1. So, with this understanding, we can now build a int n type, which behaves like the integer type, except that it has the specified number of bits that you want, and it need not be, I mean, normally you will make it a power of 2, but it need not be a power of 2, it could be 7, it could be 35, anything that you really want it to be, right. So, even it could be much smaller. So, if we want to build int n, naturally we would know that int n will involve numbers from min int to max int. These are the wraparound properties that we have already seen. So, if we take a specific example, say if we take n to be 4 bits, I want a nibble integer, nibble sized integer, half a byte size integer, then the range certainly would be minus 2 to the power 3 to 2 to the power 3 minus 1, that is minus 8 to 7. This is your min int, this is your max int, and you will have these properties that if you add 1 to 7, it will become minus 8. If you subtract 1 from minus 8 min int, it will become max int, that is 7, and if you take the negation of the min int, that is minus 8, it will be minus 8. So, these are the properties that you will have to ensure in and keep all your computations bounded within that. Otherwise, so these are the overflow conditions you will have, and just note on the below that in the literature you will often find that cases like going beyond the max int often is referred to as overflow, while getting lower than, I mean attempt to get lower than min int is often called as an underflow, but like many others like the compilers, I prefer to call both of them as overflow, because it the same phenomenon happen in both cases, that is the number of bits in the representation overflows because you are going beyond that range. So, we will consistently call both of these situations as overflows. So, in terms of this, I am sorry, this needs to be corrected, I will correct that. This is operations of int n. So, these are the limits. Naturally, if you do negation, then given that a is a proper int n, that is an n bit integer, naturally if it is within the range, then its negation would be the negative of that number, except if it is min int. In that case, it will be the min int itself, right. Similarly, if you want to do addition, then if the added result is more than max int, you have overflown max int, then your actual result will have to be obtained by adding these two and then subtracting 2 to the power n from this, because you are wrapping around. So, as you wrap around, you have a jump of minus, because the entire range is 2 to the power n. So, as you wrap around, you are coming down from the maximum to the minimum. So, you have a jump of minus 2 to the power n. So, you have to subtract minus 2 to the power, you have to subtract 2 to the power n. Similarly, if you add and find that your, because a and b could be negatives also. So, if your addition gives you a number which is less than min int in the actual algebra, then you will have to add 2 to the power n. Why? Because if you go below main int, you will have to wrap around and go up to max int, then keep coming down. So, you will have to jump up a gap of 2 to the power n. So, you will have to add 2 to the power n, that is a simple logic. And when the addition result is within the range, then you will not have to do any changes. So, these are the specific rules that of the operation int n that you will have to follow. Subtraction can be easily done by adding the negation of the second operand to the first operand. Here are some examples with and without overflow that you can use for following. In the same way, you can define multiplication, division, modulus, but I leave them as exercise for you. I mean, certainly not everything I should solve and present to you. So, in terms of the int n class, what do we get? We need a value of n which is fixed for the data type. So, n typically is a compile time constant. If n is a compile time constant, then the way I can specify n is possibly as an integer parameter for a template. So, that when I instantiate int for the first time, the n is specified and every int in my system, because n cannot keep on changing in my system, because then it will be inconsistent, right. So, I will have a template integer parameter, that is non-type parameter unsigned n, and I have just given a default value 4. Also, so this is for the interface, this is what the user will need. But to be able to implement this, I need an addition operation or subtraction operation, multiplication operation of some predefined types. I cannot keep on, I do not want to start writing from the bit level operation, that will be very inefficient also. And typically by n, what I mean is a value which is typically less than what is implemented available in the system by default. So, I want to make use of some underlying type, a type in which the actual computation will be done and then the wraparound will be applied onto that. So, I talk about an underlying type T which I want to use. I could use, for example, I could use a signed char, I could use short int, I could use int, I could use long int, and so on and so forth, right. So, as it turns out that I therefore have a template where there is one type T which by default I have kept as int. I have a non-type parameter n which by default I have kept 4, and naturally to represent the value I have a data member v of type T, right. So, this is basically my type basically my representation, and since it is templatized to be able to use this, mind you I am using a name not int underscore, because actually to be able to write this I have to write this something like int underscore int 4 like that, right. That is actually the name of my type, and it is going to be very inconvenient to use that in every time. So, what I want to do is I want to type def that to the nice name int, right. So, I want to keep that name int for the user who can type def it to this or whatever. I mean, if the underlying type is short, is intended to be short and the number of bits is 8, then the user could write it like this and type def it to int, so that int can be used, right. So, in addition we will also define two static constants, the max int and min int, because I will need them for the implementation. So, with that we can very easily implement this entire interface, design and implement the interface together. I am not presenting them separately. So, I have max int, min int. I have an explicit constructor. I prefer explicit constructor, because when the conversion is required I can explicitly do that. unless there is any reason I will use that. So, there is a default that is available, which will give me unity number, otherwise I have to give the specified number. I have copy constructor, destructor which does nothing, copy assignment operator, output streaming operator, input streaming operator, and so on. There are 2 points to note here. In the constructor, I have put 2 assert statements. Asserts are runtime statements, so that if I give a Boolean clause within the assert, then if the clause fails, then the program immediately gives a message and terminates. Since I have to be within this limit, and so if n is 4, then my range is from 7 to -8, right. So, if somebody wants to build a integer with the value default int value 9, then certainly this will not satisfy my system. So, I would like to give an assert in doing that. So, my assert says that it has to be less than maxint and it has to be more than minint, otherwise the system will fail. I do not want to use I do not want to throw an exception here, because it is not at all a good practice to throw an exception from a constructor, because then you do not know really what is happening with that constructed object, because this object is ill constructed. In a similar manner, if you look into the input streaming operator, then in the input streaming operator I am passing a already constructed int object I. So, what could have been simply this operation is is, the input stream takes I dot reads I am sorry is reads I dot v. I could have simply written that, but I am not choosing to do that. Just see what I am doing. I have declared a temporary variable v, and I have read the input value in v, and I have tried to construct an int object, and then that constructed object I have assigned to the given parameter I. The reason for that is this construction process will naturally lead to the assertions being checked. Otherwise, by this input, if I just follow is taking reading into I dot v underscore, then it will be possible to construct an object which will violate my condition, right. So, these are the nuances of data type design that you will have to remember. So, rest of these are all unary operators. The only thing to remember is for negation. If v is main int, if the value is already main int, then it remains main int, otherwise it is minus of that. Rest of the operators are same as what we did before. Coming to the addition operator, we will certainly have to do a few steps to make sure that the wraparound happens. So, we first take the values from the underlying type, add them. This is where the underlying type is important. So, these are values of type t, and this is my temporary result. And then I see whether I can construct an object of value v using my type, whether it exceeds maxint or it's less than main int. So, if it is greater than maxint, I have to subtract 2 to the power n. So, I have kept another constant pre-computed, which is 2 to the power n, a compiled constant I have computed. So, I can use it every time. Similarly, if it is less than, this is a typo again, if it is less than main int, then I have to add 2 to the power of n, right. Otherwise, it is just that number. So, this is all that is required for the wraparound. I have left the implementation of these operators onto you. You have to think through, and using this wraparound logic, you have to implement them and test them. Similarly, we can have the advanced assignment operators, which given the operators are straightforward and left as an exercise. I have a conversion operator to the basic underlying type, which will be very convenient, and then I have the different constants, and these constants I have kept in the underlying type also. So, there is a maxint which is my object, and there is the underlying value of maxint in the underlying type, that is if my underlying type is int, a value is in that, because actually I will have to do the implementation computations in terms of that. Here what I need, I will need the computation of 2 to the power n. So, there is a nice illustration of a function template here, where a function pow is being used. So, for function pow, it basically returns t n minus 1 pow times 2, right. So, it keeps on doing that till n becomes 1, in which case it returns 1. So, a call to this function given a fixed n will give you 2 to the power n minus 1, right. So, that is something which you can very easily do, and this is a very, and all these are being done in the template, because these are to be computed only once, and so I want that efficiency, as well as once this is compiled, all these values constants computed, rest of it can run very efficiently. So, with that now I have a test code which is very similar to the code we wrote for fractions. So, I will not go through them each and every line. So, we are testing different types of constructors, we are testing for reading. You can here in terms of reading, here you can give some large value beyond the maxint or smaller than the main int, and see that actually you are getting the assertions. Then we have different kinds of unary operation test, binary operation test, and so on. There are several places where wraparound keeps on happening. For example, if we see here, here is one addition which is int minus 6 being added to int minus 7. So, int minus 6 added to int minus 7 will actually be, in terms of underlying type, it is minus 13. So, since n is of 4 bits, it cannot fit in there because it is less than minus 8. Therefore, I have to add 16 to that. So, as I add 16 to that, my actual value, wrapped around value is 3. So, all these are tested out. You can check the other minus operation, logical operations, and so on. So, with that I have a nice integer type of n bits. It's great fun, and that exactly gives us a picture of how the int type works in the system. Going forward, let us do something very different. We often deal with polynomials, right. So, let us try to build in a user defined type of a polynomial. So, what is a polynomial? A polynomial is an expression like this, which has degree n plus 1 coefficients a 0 to a n, and every coefficient is multiplied by different powers of the variable of the polynomial, the independent variable of the polynomial, which is x, right. So, this is the polynomial. Given a value of x, I can evaluate the polynomial, right. So, if I want to represent this polynomial, then what are the things I need? I need to represent this coefficients, right. So, it is kind of an array, and we know that in C++ we should actually be using vector. So, I will have a vector of polynomials, vector of coefficients. Now, naturally every coefficient need to have a type, which I would like to make as generic as possible. So, I make that type as a type parameter in the template, right. There is a small typo here, there should be the word type name. I will correct this in the final slide. Now, along with that, now if we have that, then we can actually do not need, if we are using a vector, we do not need the information of degree. Why? Because in terms of this vector, I always know the size of the vector. So, the size of the vector is the number of coefficients. So, the degree has to be 1 less than that, but we will not make that assumption, and we will have a degree, data member degree also separately in the representation. The reason for that is, having that will make sure that I can even have a null polynomial of any degree whatsoever, right. So, it is not necessary that I need to know the degree from the vector, but I can have the degree and then build the vector, right. And that is always an invariant. This is always an invariant that must be satisfied in my polynomial type. Now, what are the basic operations? Now, naturally again you can do several operations with polynomial. The simplest one is I can negate a polynomial, that is negating every coefficient of that. So, that is what is defined here. A polynomial minus a x is basically when you negate the polynomial. I am sorry, there are some. So, this basically this is a wrong statement. This should be n. So, this is R I should be minus A I for all of 0 through n, right. If I negate that, I get a minus polynomial. Also, if I have two polynomials, I can add them. Now, two polynomials have degree n and m. Now, since they have degree n and m, it is possible that they are unequal. So, the resulting polynomial naturally will have a degree which is larger of these two, which is max of n m. So, in the max of n m, from 0 to let us say if we take that n is greater, m is less. So, from 0 to m, the coefficients must be added because they are there in both, whereas from m plus 1 to n, it is the coefficients of the larger polynomial which will only exist because rest of it is 0. So, this is how it is defined, that if I add these two polynomials, then up to the smaller degree the coefficients are added, then the remaining coefficients of the larger polynomial is basically put at the end of it, and this is the definition in terms of the coefficients. And since we can add, we can negate, we can do subtraction. Obviously, we can define multiplication of polynomials. Division of polynomials are relatively more difficult because a polynomial may not divide another polynomial totally. It might be an infinite process or it has to be defined in a different way. So, but at least multiplication can be defined, and I leave that as an exercise. But with this itself we can do quite a lot. So, what is the UDT that we have? I have a polynomial constructor which takes a vector of coefficients and build the polynomial. By default, it takes a vector having a single value 1. So, by default you can have a polynomial having just a constant 1. So, this is your default as well as parametric constructor, or the polynomial may just take the size, just take the degree n and build the polynomial, which is a null polynomial. So, you put n to degree and do a coefficient vector of n plus 1. If you do that, then it naturally means that all coefficients are 0. So, you get a null polynomial of nth degree. Other than you can copy construct, you can copy assign, you can destruct, of course, that in turn basically destructs the vector by calling the destructor of the vector. This is the sign preservation. This is the negation of the polynomial. So, you are simply negating. This is the add operation. So, you first take a result polynomial as a temporary, and then what you do, you compare the degree of the two polynomials, the current one and the one that you are adding, and you check which one has a higher degree. Whichever has a higher degree, you copy that to the result, because the result is going to have that degree. You can see that we have already created this result polynomial as a null polynomial, right. That was what was the purpose. So, we choose depending on the degree, we copy the larger coefficients of the larger polynomial into the result polynomial, and then we copy, then we add the coefficients up to the smaller degree from both the polynomials and put it to the result polynomial, right. So, this is the simple addition. just the formula we wrote, we are just implementing that. Similarly, you can do a subtraction here. So, you can have plus assigned, minus assigned operators based on that, and then you can write out a polynomial. This code looks a little bit clumsy C, because possibly that is the best way to write it, because there are several special cases you need to take care. For example, if a coefficient is 0, you do not want to write that term. If a coefficient is 1, you do not want to write 1 in place of that, you just want x to the power that. If say your constant is 0, then you just would not write that constant, and so on and so forth. You do not want to write if constant is 5, you do not write it as 5 into x to the power 0, you will just have to write it as 5. So, these different cases are checked, and this is just a simple logic based C kind of program for output streaming. Similarly, you have input streaming, which is simpler, and finally, you need a function to evaluate the polynomial. So, what I do is instead of giving a different function, I actually overload the function call operator. So, this is a polynomial UDT, which is also a polynomial functor, right. So, that if I invoke the polynomial in this class, if I invoke the function call operator with any given parameter value, then the polynomial will automatically get evaluated, right. So, you can see how things are setting up together. Here are the data members, 2 convenience functions, mean and max. If you use, you can also use library functions from standard library, but I just wanted to keep everything within this class. So, with this you can write the test code, building different, constructing different polynomials, reading polynomials from input, negating polynomials, adding polynomials, subtracting polynomials, and so on. And if you note, let me just go back. If you note, then all these polynomials I have done, I have taken it to be polynomial of integers. So, integer coefficients, and naturally you will do an integer evaluation. But interestingly, that where you can now make things mixed is you can make use of the fraction class that we have already designed and make a polynomial of fractions, that is where coefficients are fractions, even the value that you evaluate with is a fraction. So, if I define say I define a vector of 3 fractions, 1 by 2, minus 3 by 5, 2 by 3, and construct a polynomial. If I print it, this is what I get: 2 by 3 x square minus 3 by 5 x and 1 by 2, right. And if I evaluate this by the functor for 2, I get a fraction. So, now everything can happen in fraction. So, you can see that we had built a fraction class, fraction UDT, to operate only with fractions. We have built a polynomial UDT to operate of polynomials of various types, and now we are using the fraction to use in a polynomial. So, I can have a polynomial with fractional coefficients and fractional value. I can use my limited size int also to define fraction. I can use polynomial of int n sized numbers and so on. So, there are several ways these things can be mixed, and in the practice UDTs, I am not going through the slides. I have given a number of problems for you to design and practice and try out. So, to summarize, we have presented the design, implementation and testing for int n, limited size n, integer, signed integer, and a polynomial type of based on any coefficient and value type. And we have showed how poly int and poly fraction works, and outlined several practice UDTs for homework which you should try out. And with that, I think you will get a good command over doing data types or writing classes in C++. Thank you very much for your attention. Meet you in the next session.